How's it going, everyone? Stefan here, and today we're going to be talking about calculating the number of pump passes during a TFF operation. So like the reason this is important is because, oftentimes your solute or your protein, whatever it may be that you're, concentrating or diafiltering, can be sensitive to shear. And, as you're doing this operation, this TFF operation, right, you're pumping liquid across this filter, and because of the retentate valve that adds back pressure, some gets pushed across the filter, but the rest is returned. The rest of the liquid is returned, and the solute, and then this keeps going on for some time, right? And there are many passes made, and over time that can damage your protein and or solute, causing like aggregation or fragments, and loss of activity. So it's good to track your pump passes, especially during like early development, so you can see what your product is capable of handling, really. The expression for pump passes is given here. So in what we have is the integral of the feed flow rate from the pump over the retentate volume. So it seems pretty simple, but really this VR is a function of time when you're doing concentration, right? Because as you're concentrating, your permeate volume is increasing. That means your retentate volume is decreasing. For something like diafiltration, it's pretty easy, right? Because now you're adding diafiltration buffer in at the same rate. You have that, we'll call it QD for the diafiltration flow rate is going to be equal to the QP. And this level will stay constant. So then in that case, the calculation for I'll write it over here, for the number of pump passes during diafiltration is easy. It's the feed flow rate QF times, if you did the integration, times the time of diafiltration all over the retentate tank volume, and that's constant. So this becomes really easy. And I mean, this makes sense, so like, you can think of like if you had 10 liters as your VR, 10 liters in your retentate, and your pump feed rate is 1 liter per minute, and you pump for 10 minutes, you've pumped a total of 10 liters, which is how much you have in your retentate tank. So all of that volume has passed through the pump one time, hence one pump pass. But it gets a little trickier than during the concentration steps. So there's a few different ways you can calculate this. One way, it gets you a pretty reasonable result is like during your concentration. We'll call, oftentimes concentration is referred to as ultrafiltration. So I'm just writing UF. You can say that the number of pump passes is equal to the feed flow rate times the time of the concentration, and then do something as simple as take like the average volume. I'll call it VR1 and VR2. You could call them initial, final, whatever you want. But like you could do something as simple as that, and that gets you a pretty good result. But there's two other ways that we're going to go over calculating this N. And then, of course, actually, I'll note that, like, your total pump passes are going to be equal to the sum of, like, all the steps, where, you have a concentration step, UF, you have a diafiltration step, DF. You're going to add all those up, that's how you get your end total. But first we'll go over, a solution that I don't know who came up with it, but we'll get started with that. And it uses this equation here and is for, the situation where, or I guess that accounts for like a diafiltration and a concentration. So we're going to go over that now. First, I'm just going to like circle these so we know this is like one way. We'll put a 1 like that. And now we're going to go over the second way. So the second way makes use of a couple special little definitions. So the first is that Y, the conversion factor, is equal to your permeate flow rate over your feed flow rate. So it's just the fraction of your feed that goes into the permeate. That's Y, your conversion factor. We'll also make note that how do I want to say this? Okay, so there's two other definitions we're going to write here. So the change in your permeate volume is going to be equal to the negative change in your retentate volume during concentration, right? Makes sense. As you collect volume in your permeate over here, you're losing it from your retentate, and that level goes down. That's also just like such a bad R. Okay, so the final definition we have here is that the rate of change of your permeate volume is just going to be equal to the permeate flow rate, right? Makes sense. Okay. So now we can start plugging some of this into this equation up here. Okay. So first we'll start by we can rearrange this Y. Let me see if I can just copy and paste this down here so we have that a little closer to us. Okay, cool. All right, so continuing on here, sorry about that. We're going to rearrange this conversion for F and plug it in to our equation. So we'll have 0 to T, and then that's equal to QP over the conversion factor Y, DT, and then VR. And then you'll notice, if we brought the DT over next to the QP, we can, plug that into our expression again. And now we can write the integral of, like this, and this QP DT will become dVP over VR. And, it would change the bounds from 0 to the final permeate volume. But then we can make use now of this last definition here that is saying, the change in our permeate volume is equal to the negative change in the retentate volume. And then that's going to change our bounds again. So the conversion, a sneaky thing about this is we're assuming it's constant. So I'm going to pull that out of the integral. And then I'm going to write this. We have negative dVR over VR. And then this is the bounds are going to be V naught to V. That's like the V final. I guess we can put an F here. And then another thing is, outside of the integral, we can add just n, and then it's accounting for dye filtration and the number of dye volumes. And I'll let you think about why that makes sense a little bit, but without going into too much detail. But really, it should be kind of straightforward, right? Like a dye volume is uh, equal to the volume in your retentate during a dye filtration, right? So, like if you do one dye volume, you've pumped all the volume in your tank through the pump one time. So that makes sense. So now we can just solve this integral. We've seen this before. So we're going to have 1 over y, negative 1 over y, is the negative here. And then we'll have the natural log of VF over V naught plus n. And now this here is your solution, but as always is the case, you might not see it that way out in the world. So we'll do a little rearranging. Can write natural log of VF over V naught, over V naught. Leave this conversion out here, right? Negative 1 plus n. And then, because this is a negative 1, we've gone over this before. This is the property of that. So we can pretty much take the reciprocal of like this VF over V naught. And remember, the concentration factor, we've seen this before, is equal to V naught over VF. So then finally, we can write all of this as 1 over y times the natural log of the concentration factor plus n, and that's equal to your pump passes. It's so hard to write with this mouse. Pump passes, and that's also equal to the little n. Yeah, so I'm going to circle this. So I'll put a little 2 here. This is the second way you can calculate your number of pump passes. And now I'm just going to bring this back down. If I can select it. Let's get this. So now we're going to discuss the third and final way to calculate your number of pump passes. The first two that we've gone over, are sufficient for pretty much all purposes. But I have another way, number 3. Get this in red. Number 3, and it accounts for this being a function of time. Pretty much what I have done is, I have an Excel file for my run, which I'll show you in a second, but it just describes how the permeate mass, so call this M permeate, or like the volume of the permeate over time changes, okay? And, oftentimes the way this looks is like, as you concentrate your material, your flux slows down, so you collect less permeate mass over time. So you kind of get like a logarithmic sort of shape. Okay. And what I have done is I've used Python to, create a log function that is, you know, telling me my permeate volume over time. So I use Python to get this as a, it's a using a log function. I fit a log function. And then of course, like, our V total minus the permeate volume over time gives us a retentate volume over time. Okay, so then with this expression, I can integrate it again using some packages available in Python. I have the QF, and then I also have the time um, of like my concentration steps or my diafiltration steps, and I can calculate the number of pump passes. So first, I'm going to just share uh, my Excel sheet so you can see what that format would look like. Okay, there it is. So hopefully you can see Excel right now. And when your TFF systems, you'll generally record like a permeate mass and and a time. So I pretty much have time in minutes and then permeate mass in grams. And then I've also just noted what the step is as UF1. Let's see, okay, into DF, and then finally UF2. Okay. And to like make those notes, like oftentimes the TFF softwares will like let you make that note, or you can maybe write a script that like looks for a permeate volume when you switched from concentration to diafiltration or whatever. But to use my script, you're going to need a file that is in this format. So again, you're going to have time labeled as time. You're going to have the permeate volume labeled as M permeate. And then you're going to have this step. You're going to note in the side that the step is either UF1, DF, or UF2. Okay, so now I'm going to share the script. Maybe. Okay, there it is. Again, so you feel free to pause the video and you can copy this script and use it for your own experiments. This is a file that I have like some different functions for TFF. And so like I've written it as a function and we'll run it over in this untitled 0. I'm not going to go through all of this, but just generally, it asks for the file name, your initial volume, and then of course your pump flow rate FR. And it's important to list in that third column the steps, because like what this is doing is it picks out the step that looks for UF1 so that it can fit a curve, the log function to your permeate mass over time, and then integrate that function. For the diafiltration, it calculates it differently. Here, it's just using that basic calculation I showed in the very beginning, where you just have the feed flow rate times the time of diafiltration divided by the retentate volume during diafiltration. That calculation is super easy. And then it finishes up with the UF2. So it looks for that UF2. So it's important to have those. So I'm just going to scroll through this again. So you can copy it if you'd like. And, of course, change I'm no master programmer. So this might, I see some of this is cut off actually. Just make sure that wasn't the case up here. Okay, so pump passes function starts here. You'll notice I have like some functions inside the function. I don't know if that's good practice, but that's what's going on here. So yeah, keep scrolling down. And then down here, this is the end of the function. I just have some different plots, which we'll see here in just a second when I run this. Yeah. And one thing I'll note is that like if you use this, make sure you save the file in the same location as the script. Because the way this is set up is that they're in the same path, like you can put the full file path in this function and it'll find it, but I don't have that set up here. So just want to note that. Okay. So I've imported the file that has all my TFF functions. And then I call out the pump passes one that I was just showing you. I'm saying that we're starting with 1,120 milliliters and pumping at 79.5 mils per minute. I can run this and we get a few different plots here. Also, I'll just point out I have it set to output the total number of pump passes for each phase. So like we can see that for UF1, there's 5.9, or excuse me, 5.39. Diafiltration, there's like 38.7. And then for the second ultrafiltration step is really short. There's only like one pump pass. I have a bar chart output that shows those numbers we just went over for each phase, as well as then it adds them all up to get the total. And then here we have the pump passes over time. So there's not a ton of flux decay. So like during the first concentration, so like you see this line is pretty linear, I guess, but I'm going to copy this. We're going to go back to the whiteboard just so I can draw on it in a minute. But if you saw more flux decay, this number of pump passes would start increasing exponentially. And then this orange line is diafiltration. It's linear there. Your flux is generally constant during diafiltration. It can change depending on like if your protein's happier in the buffer, the diafiltration buffer, or maybe it'll go down if your diafiltration buffer is more viscous. It can change, but it'll often stay pretty constant, which is what we see here. Stays flat. And then the second concentration is so short that it also stays flat. These are the curves that I fit. Where like this is technically the log that I was talking about. So, and this is for the I should probably have a title on this, but this is for the second concentration step. You can see that it's like really short and it stays pretty flat, and it really just looks like a straight line. However, for the first concentration, you can start to see it taper off a little bit here. So what's nice with that log function is like if you have not a lot of flux decay, you can capture that linear section. Your log function will change, but it'll still be able to be modeled by that log function. And then if you get a lot of flux decay, you're also going to capture that situation. So that's why I like the log function. Maybe you have a better one to fit your data to. But real quick before we wrap up this video, I'm going to go back to the whiteboard. To a new whiteboard. I've had issues with this where I can't get my pen back, which is annoying. So I don't know if I'm going to be able to here. Yeah, for some reason I can't do it. But anyways, I'll just use this laser. So, what I was saying, I just wanted to draw quickly. If you get a lot of flux decay, your pump passes, like this is the first concentration step, um, what you'll get what you'll get with a lot of flux decay is you'll see something like this. Like your number of pump passes will increase really quickly, um, and then they'll probably be linear at. Wow, that's so bad. Um, they'll stay linear during diafiltration, and then like if you have a big second concentration, maybe they'll start increasing exponentially again. So it's just some behavior you might see. I hope that this video was helpful for you. And you can use the script that I showed in here to, model the number of pump passes over time, or you can do something as simple as like, the using like the average volume in the retentate tank and doing a simple calculation. I've checked, and they're pretty close, especially if your pump passes over time, like this plot here. If that curve is pretty linear, that approximation is going to be even more accurate. But if you get a lot of that exponential behavior I was just describing, that approach of taking the average volume in the retentate won't work as well. And then there you might be better off using something like the second method I showed, where you have like the natural log of the concentration factor plus the diavolumes times or divided by the conversion factor. So these are just some different ways to calculate pump passes. Let me know what you think. Hopefully this was helpful. And yeah, catch you all later.